Welcome to the 9th of 14 videos on the Arc Flash Truth No One Explains. My name is Joe Chacon. I'm the president of Podge LLC and Chacon Engineering. I'm a licensed professional engineer in multiple states and have been an electrical engineer for almost 30 years. Please like and subscribe as this helps us get this important information in front of more people. This video is going to walk through an example for a DC arc flash. Remember, IEEE 1584 does not address DC calculations, but they are quite important, especially in the photovoltaic or PV and battery energy storage spaces. I hope the standard that is addresses this in future standards, the IEEE 1584. For now, we have to defer to NFPA 70E Annex D5. That standard and that annex provides the governing equations that are known as the maximum power method. You can already see this is significantly less complicated than the IEEE 1584 standard. For instance, arcing current is simply defined as 50% of bolted fault current. Also, there is literature that suggests this maximum power method is overly conservative. I like this. Remember, DC behaves very differently than AC for many reasons. Although DC arc flash hazards are generally less severe than AC arc flash hazards due to differences in arc sustainability, DC systems typically present a greater shock hazard than comparable AC systems. Let's dive into an example. Consider a battery energy or battery storage system that has a voltage of 1000 volts DC and can deliver 100,000 amps of bolted fault current. We immediately know the arcing current is 50 kA because of the first equation. We do need to calculate the clearing time, though, for this application. I, as in previous videos, will not show how to calculate the clearing time because that can be an entire video series by itself. So exercise caution because DC is different than AC. And as a hint, look up I2T curves for DC fuses. All right, let's assume we did the math and the arcing time is 20 milliseconds. Also, assume the electrician will be working 18 inches away or 45.72 centimeters. This is the values that were plugged into the Annex D5 equation, and the result is 4.78 calories per centimeter squared. Now, assume the clearing time is significantly more than 20 milliseconds. Suppose it is 3,000 milliseconds. So, often engineers will clip the maximum clearing time to 2,000 milliseconds, even when the clearing time is significantly higher than 2,000 milliseconds. This practice is often justified. So, the answer would be 478.4 calories per centimeter squared for 3,000 millisecond clearing time, which we clip the 2,000 milliseconds because we know we can justify that. Notice the plot I created to show how the maximum power method for DC sharply rises, and then I clip that 2 seconds and beyond. How do we calculate the arc flash boundary? Well, remember, that is simply the boundary at which incident energy is 1.2 calories per centimeter squared. We make 1.2 calories per centimeter squared our incident energy and then solve for D. That will be our arc flash boundary. I took the liberty of doing that. The answer for our example comes to 91.3 centimeters or 35.9 inches. The last thing I want to say is these equations are only good for up to 1000 volts DC. So, what do you do on these modern systems that are as high as 1500 volts? Well, the short answer is to use the equations as they are. The software I use actually asks you, as the user, do you want to use the same Annex D5 equations when the known system voltage is higher than 1000 volts? Our next video will be about the Ralph Lee method, which was the method that started it all. I'll instruct on that method and when to use it, as we know IEEE 1584 has its limitations.